A very warm welcome for my session on IV characteristics for series and parallel connected PV modules. As all you know that normally a PV modules is operated around 40 or 50 voltage and a current of 5 ampere. But the load demand will maybe of order of very higher voltage, may say example that it may be a 230 volt, 100 volt or maybe 400, and the current rating is also much higher than that of the rated of the PV. So in that case, to match the load, PV modules are connected in series and parallel to match the loading condition. So in this lecture, we will be able to see that how the IV characteristics will be there if these modules are connected in series and parallel. And this is the overview of my presentation. So we will see the IV curve for a series connected PV modules, a parallel connected PV modules, and an array. In case we considering that the PV modules are of identical in nature, but in practice that the characteristics of two PV modules may not be similar. So what will actually happen that if we actually connect two PV modules which are having a dissimilar characteristics, and there are some effects which will happen during the series connections of PV modules, so which actually also will be seeing in my course of my presentation. So to explain the IV characteristics and the PV IV and the PV characteristics of the PV module, I have considered a 250 watts peak panel. So this is a 250 watts peak panel which has an open circuit voltage of VOC and a short circuit current of 8.64 ampere. So if you see, this is actually the IV and PV characteristics of the PV panel. You can see there are three significant points which you would have marked in the I characteristics of the PV module. So the first is the open circuit voltage. So the open circuit voltage, so where there is no load actually which is being connected, that means the current which is actually connected to the system was actually zero. So this is the current line, zero line, and this is actually the operating point is the open circuit voltage of the PV module. Whereas there is another one, so where the load is actually shorted. So if it is shorted, it is a voltage zero line, and this is a voltage zero line, and this is the operating point, and this is the short circuit point. That means the resistance which has been getting connected to the PV panel was almost zero, so dead short. So at that particular time, the PV panel will actually carry a current of short circuit current, and this particular case it was 8.64 ampere. And another significant point, it was BMBP and IMBP. So this particular panel will like to give the voltage, the maximum VMBP voltage is 30.72 volt, and the current was 8.14 ampere. So if you try to vary the load between from what, say example, from 0, R is equal to 0 to infinite, we will be able to get different operating points over the PV characteristics. So this particular IV characteristics is the characteristics of the PV panel, which is actually at a standard test condition at 1000 watt per meter squared and at 25 degree Celsius. So this is the PV model which we have considered to study how the IV characteristics and the PV characteristics will change or may be when they are connected in series. So here the two modules are connected. One is the module 1, this is module 1, and this is module 2. So module 2, there are two modules are connected in series, and this is the characteristics of the PV module. So PV module, and the assumption which we have considered over here is two modules are identical in nature. It means the characteristics of the module 1 and module 2 are same. In other way, the irradiation which is actually there in the module 1 and the irradiation in the module 2 are similar, and the temperature is also same. So that's the assumption. So they are connected in series. So if they are connected in series, then we know that the I string, so this is the equation which will be I string, the string current. So this is a string current. So the string current will be equal to IPV1, and the string current will be equal to IPv2 because the current in the series circuit is actually same. So the I string is equal to IPv1 plus IPv2. Whereas VPv1 is the voltage across the PV module and VPv2 is the voltage across the module 2. So now we are interested to see how does the characteristics of the string looks like. So string. So how to find out the string characteristics? We have already seen three significant operating points. So what are the three significant operating points? The three significant operating points are, one is the open circuit voltage. This is a one point. So another point is actually here. So we'll just see that how to do that. Okay. So as per the law, as per the Kirchhoff's voltage law, the voltage string, the voltage across the string is VPV1 and VPV2. So in VOC the current is 0. So the current was 0. So if the current was 0, then the voltage across the string 1 is VPV1 and the other one was VPV2, which they are similar. So and now the string will be 2 times the module voltage. So this is the operating point. This is actually the operating point. So of the string when actually they are connected in parallel. So this is the case. So 2 times the PV1. So similarly, you can actually connect for any current. We can draw a current line, find out this particular point, and then we can actually convert that into 2 PV1. So similarly, we can actually make different operating point at this point, and we will get a curve. So that particular IV curve is the IV characteristics of a string which actually carry 2 PV modules. So V string is 2 PV. So finally it is V string is 2 times the VPV1 and I string is equal to IPv1. So by varying different currents, from the current from 0 to 8 and marking the voltage 2 times that of what it was, we will get the IV curve of a series connected PV modules. And what is the assumption which you have made is the assumption was these 2 PV modules are having identical characteristics. That means they are actually same. Okay. Then we will see how does an IV curve for a parallel connected PV cells will look like. So here, so there we have actually seen, it is a series connection. So here it is a parallel connection. So in case of a parallel connection, so which is the case, the V string, the voltage across the string is equivalent to VPV1 and it is equivalent to VPV2. So the voltage across the module 1 and module 2 is equivalent to the string voltage. Whereas the current which is in the string is a sum of IPv1 plus IPv2. So that's the Kirchhoff's curve. So now if I want to draw the characteristics of a parallel connected PV modules, so you can draw lines from here. So you can draw lines for a 10 volt, you can draw a line from this 10 volt. So you will find out, so actually what actually the point was, this is the point. So this is a operating point at 10 volts. Okay. So now what will be the string current? So the string current is 2 times that of an IPv1. So you can mark here. So this is 2 times the IPv1. So you can mark here. Similarly for 20 volt. So from the voltage you find out this, you mark here. So you can actually mark different operating points like this, and then at last you will get a IV curve which is actually given by this. So in this IV curve of a parallel connected PV modules, the voltage across the string is equivalent to the voltage across the module, whereas the current was actually doubled. Whereas in case of a series connection, the voltage was doubled and the current was same. And in both the cases, we have assumed that the 2 modules which we have considered as identical characteristics. So now we'll to see that what will happen if I connect 2 modules in series and 2 modules in parallel. Okay, so I hope that you can easily answer it. So when there are two modules are connected in parallel and two modules are connected in series, you can see that the voltage will also be doubled. The voltage will also be doubled here, and the short circuit current will also be doubled. Okay, so VPV1 is equal to VP2 and IPV1 is equal to IPV2. So they are actually the string currents, not actually the module currents. They are string currents. So VPV1 is equal to VPV2 and IPV1 is equal to IPV2, whereas V array is equal to VPV1 plus VPV2 and I array is equal to IPV1 plus IPV2. So this is how actually a IV curve for an PV array will looks like. But in all the cases, what we have considered is the modules are identical in nature. But is these IV characteristics of the PV modules will be identical in practice? In practice, there may be a possibility that the IV characteristics of the two modules may be dissimilar. Okay, so it may be due to a difference in cell processing, or maybe two processing because of the processing technology may be difference. Cell modules of same rating but different manufacturer, but normally this is not preferred actually. So if someone has connected modules of same rating and but a different manufacturer, there is a possibility to occur, but these are very minor. The third was actually the different outside condition. That's the partial shading of the cells. So this is actually will affect actually the characteristics to a larger extent, because you would have studied that the IV characteristics or the short circuit current is actually a function of irradiation. So in case if there was a shade which is actually sitting in one module, the short circuit current of that particular module will actually vary very largely than the other one. So that's one point where actually so the characteristics of the PV can be largely varying. So between two panels. So partial shading is one of the thing, and maybe sometimes when they are actually installing the PV modules, the inclination which they have kept between two modules may also be different. So that is also one of the places where actually we would be able to see how the IV characteristics of the two modules may be different. So we will see how does the IV characteristics will be when two modules which has dissimilar characteristics are connected in series. Okay, so there may these are the two things which we have drawn. So you can see that one is at 1000 watt per meter squared, another one was 8000 watt per meter squared. So you would be able to see there is a large change in ISC. So there is ISC, whereas this ISC was different and this ISC was different. Similarly, you would be able to see that there is a difference between these two. And normally, in case of a PV system, we like to operate in this particular region. This is a particular region which we may try to operate. So you would be able to see that dissimilarity in the ISC will affect the PV system to a larger extent. Whereas the dissimilarity in the VOC was actually very minor. So we will like to see that what will be the effect if actually these characteristics of which the modules which have two dissimilar characteristics are connected in a series. Okay. So we have already seen how to draw a IV characteristics. So when they are actually similar, but here only thing is you will be able to see that these are two panels. So this is actually a module 1 and this is module 2. So let us assume that this is a module 1 which is actually 1000 watt per meter squared, and this is module 2. So from this you will be able to observe that the two IV characteristics are not similar. So why it is not similar? Because the irradiation which is actually there on the system or which is on the module are different, maybe due to some effects. So now we are connecting these two modules in series. Okay, module 1 and module 2 are series. So we know that in a series connected modules, the current is same. There will not be any change in the current. So the I string current will be equivalent to, so the I string current will be equivalent to IPv1. So I string is equivalent to IPv1 and is also equivalent to IPv2. There is no doubt about it because it is a series. So all the current has to flow like this and it has to go. So they are actually similar. Whereas as it is a dissimilar modules, the VP1 is not is equal to VPv2. So now what is the formula? How to find out V string? How to find out V string? So V string is VPv1 plus VPv2. Okay, so we will see. So now how to find operating point over here? First we can draw for current. When the current is 0, when the current is 0, you can draw a line like this, draw a line like this. Now we go from where it actually cut in this axis, we will be able to find out what is VPv1, what is VPv1 and what is VPv2, and the string current is sum of these two. So VPv1 plus VPv2 will be almost equal to 74.5 volt. So this is one of the operating point which we like to draw. Similarly, we can draw for other operating points. So this is a place. So this is the current operating point. So you draw a line. So draw a line. It cuts here for VPv1. So VPv2, and this is for VPv1. So one is VPv1 is 35.1 volts. Another thing is 32.9 volts. If you add this, you will get another operating point of 68 volt here. Okay. So similarly, you can actually plot the curve by changing the currents, by changing the current in the system. We would be able to draw a different actually plots. And so this is another case. So where it is equivalent to, this is a very important point. We can see that. See here, this is a particular point where actually it is equivalent to the ISC of the shader models. So this is the point where it is ISC of the shader models. So when ISC of the shader modules, you can see that what is VPv2? The VPv2 is 0. So the VPv2 was 0, whereas VPv1 was 33.4 volts. So the voltage across the VPv2, that is in the shader models will almost become V is equal to 0, and the string voltage will be equivalent to the voltage which is across module 1 if you try to operate at the short circuit current of module 2. Now there is another case. What actually will happen? This is a very important thing which you want to understand. What will happen if I try to increase the current beyond the short circuit current of the shader modules? Okay, so to know that, actually we want to extend the IV curve of any given IV curve along the x-axis. So this is what the extended line of the characteristics. So now we will see what will happen if I like to have an operating point which is more than the short circuit current of that of a shaded models. So this is actually the current which is actually more than that of the shaded current which I like to operate. So or maybe this is the operating current which I want to share. So if I draw lines, you see here lines, we will get an operating point at VPv2. So VPv2 we are getting an operating point, whereas the other line is cutting at a voltage over here. So we would be able to see that the voltage across the VPv2 is minus 31.8 volts. Minus 31.8 volts. So what does it indicates? That if you try to operate the string current more than that of the short circuit current of the shaded module, the voltage across the shaded module will become negative. So what does it mean that the voltage across is negative? The current is positive and the voltage is negative. So what about the power? The power was negative. The power was negative in the shaded modules. As the power was negative, instead of acting as a generator, instead of the PV module acting as a generator, it is acting as a load. So the shaded module is acting as a load and it will try to dissipate heat in the shaded modules. So if you allow this to continue further, the module will continue to get heated and it will try to burn. This phenomena was actually called as hot spot formation in a PV array. So what will happen? A shaded modules will actually kill itself. So when actually it was being kept in a shades. I hope that you would understand the formation of the hot spots and how actually the voltage across the shader model will become negative. So here what you understand is we know how actually to draw the VI curve of PV modules. So this is actually the curve of the PV modules. So as you point, so the curve is actually given like this. So this is actually the IV curve of the PV module, and we understand that if you increase any current further more than that of the short circuit, the voltage across the shaded module is becoming negative and it's getting heat.